All right, so let's pick up the lecture from where we left off in the last class. So we're talking about structures. So remember, with structures, when you assign a variable that is a structure, or you assign a value to a structure, you're actually copying the other structure bit by bit. And so when you pass a structure to a function or return a structure from a function, right, you're not passing the actual structure object, but you're passing a copy of the structure object. And so this has some implications on when you on what you can do with a structure object when you pass it to a function. All right, so here's our structure point 2. Right, it's got an x and a y coordinate. Here I've got a function called move that takes in a structure, a point 2 structure called t. And all it does is it adds 100 to the x and y coordinates of t. Right, so it just shifts t by 100 and the coordinates of t by 100 and 100 in the x and y directions. Right, so it takes t, adds 100 to x and y. And here we're going to print out the coordinates of t. So if t came in as 0, 0, when we print it out, it's going to be 100 and 100. Now here we also return t back to the caller. However, someone who is using move, they might expect move to change their structure that they passed to the function. So here's our structure p. It has coordinates 1 and 2, right? And the caller here is calling move, presumably to move p to 101 to 201. Right? So they're expecting the coordinates of p to change. Unfortunately, the way that structures work, this doesn't happen. Right? So p before the move is 1, 2. Right? Inside the function, right, t really does change to 101, 102. Right? In other words, 100 really is added to 1 and 2. Right? But after the move, right, p is still 1, 2. So p didn't actually move. Right? And there's nothing wrong with the function move. It's just the way that structures work. Right? When we call move, we pass a copy of p as the argument to the function. Right? So move gets a copy of p. It doesn't get the original p object. When it adds 100 to the x and y coordinates of t, it adds 100 to the copy that it got. Right? And so that doesn't work. So one way to remedy this is to return a copy of the structure yet again. Right? So return t back to the caller. Right? And now the caller, when they call move, they can call it by writing p equals p move. So reassign the returned value back to p. Right? And now when you do that, right, that in fact, it doesn't change p. Right? It doesn't change the original point. Right? So remember what's happening here is that you are reassigning a value back to p. Right? So you're overwriting the existing point. So that's one way to deal with it. Right? You can force or require the caller to reassign back to their variable. Right? If they really want their, if they really wanted their variable to change. Right? The other way to deal with this is to rewrite move so that it takes a pointer to a structure. Right? So in other words, to do something like the following. So star, right? We have to call this something else. So we're going to have to call this, I'm going to call it shift. Right? Because I can't have two functions called move in the same compilation unit. Right? And so here, the caller passes in, uses a pointer to a structure to call the function. Right? Now I have to dereference the pointer to update x, right? Or use the arrow operator because I have a pointer to a function, pointer to a structure. Sorry. Right. So whenever I access the x and y coordinates of the structure of the pointer, I'm going to use the arrow. Right? And here I'm going to return back a pointer. So now I can return back t. Right? And so now if you call shift here, sorry. So instead of calling, instead of using reassigning back to p, right? I can shift p, right? This time passing in the address of p, right? And then hopefully, yes, that does in fact cause our point to move now, right? So you can either right? So either rewrite your function so it takes in a pointer to the object that you want to change, right? Or force your caller to reassign back to their object, passing in a regular structure rather than a pointer to a structure, right? If your structure occupies any significant amount of memory, you should probably pass it by pointer instead of passing it by value. Right? If you pass it by value, then the C has to make a copy of the structure to pass it and return it from the function. Right? And you want to avoid passing around large amounts of memory if you can. Right? By passing in a pointer, you're just passing in a pointer, so probably 8 bytes on your computer. Okay, so once you've shown someone what a structure is, one of the very first things that occurs to somebody is that, well, I've got this structure in C. Arrays don't remember how big they are. So why don't I just create a structure that has an array and the size of the array as 2 of its members? Right? So you might want to make the following array structure that represents an integer array, where the structure knows how big the array is. Right? So size is the length of the array, right? And there's your array of int that can hold size elements. Right? This sounds like a good idea. Unfortunately, it doesn't work in the language. It doesn't work like this in the language. There's a way to do it. You just can't do it this way. And so the reason you can't do this is because C doesn't allow you to have a structure whose size is not known at compile time. Right? The way that structures are defined in C is that the amount of memory that's required for an object is equal to the sum of the memory of its members, right? Plus some additional padding. So you're allowed, the compiler is allowed to insert space between this member and this member. And so for this to work, the compiler needs to know how big is the structure at compile time, right? If this is a variable, and it is in this case, right, that's a variable length array, so the compiler can't determine how big the structure should be at compile time. So you're not allowed to do that. What you are allowed to do is the following. So the last member of the structure is allowed to be what's called a flexible array member. So it can be an array where you don't specify the size, right? But array is an array, right? And its array, the size of the array is allowed to change. Right? So this is allowed. And so you could create your int array this way instead. Right? There are some other restrictors on structures that use flexible array members. Using these things is a bit awkward. So I normally don't talk about how to do this, how to use this form of a structure. The easier way to deal with this is to have a pointer here instead of an array. And we'll talk about that when we get to the arrays notebook, which is coming up next. All right, so that wraps up our discussion of structures. Right? They're sort of, but not quite the same as Java classes where everything is public. Yes? This one? Yeah. Yeah, you have to allocate. So this is the problem with this one. You have to allocate memory for this thing yourself. And so we don't know how to do dynamic memory allocation yet. So I can't talk about how to use one of these things at this point in time. Yeah, but that's the problem, right? So yeah, you need to allocate memory for one of these structures on your own. Yeah. But arrays is the next notebook. All right, so the beginning of this notebook is a lot of review. Right? So I'm just going to skip over the top part here and just very quickly review using arrays. All right, so this example here should be familiar or easy to understand for all of you. Right? That line there says that x is an array of 3 ints, right? And the values of stored in x are indeterminate. You don't know what values are there, right? They're uninitialized. So they could be anything. Right? So here I'm just going to set the values of the first 3 elements of x, and it does exactly what you expect, right? X has the values 0, 1, and 2. Right? So if you run that, 1, 2, and 3. So it's 1, 2, and 3. Right? Okay, so if you don't set the values yourself, and if you don't initialize the array, when you print out the elements of x, so there are 3 ints, right? There is an array, it has 3 ints. You just don't know what their values are. So here, when I print out the values of x, right, we get some seemingly random values. Right? I don't know if you get the same values every time. No, you get slightly different values each time. Right? And exactly what these values are, you can never tell. Right? So uninitialized array, values could be anything. Right? If you want to initialize the array, you can do so like this. Right? If you don't specify the size of the array, then the size of the array is just or the length of the array is just equal to the length of the initialization list. Right? So here X is an array of length 3, and its values are 1, 2, and 3. Right? If you do specify the size of the array or the length of the array, then it's an error if you use more initializers than there are room for you in the array. Right? So here I've used 5 initializers, but the array can only hold 3 elements. That's an error. The compiler will actually flag this. Right? So warning, warning, warning. And I'm pretty sure. Does it actually run? I don't know if it actually runs. Here, this looks like the compiler is issuing a warning, but this is an error. Right? You're not allowed to use more initializers than there are elements of the array. You can use fewer initializers, though, if you like. Right? Which one? There's a number missing here somewhere. There's supposed to be a number here. There. Okay. So that says X is an array of length 3. Right? And that says its first value is equal to 3. Right? The remaining elements are uninitialized as far as C is concerned. So if you run that, so here we get 0 and 0, but you're not guaranteed to get those zeros and that 0 and that 0. Right? The remaining elements really are uninitialized. And finally, if you really want to, you can specify the indexes of the values that you are initializing. You can click on that link there if you'd like to see the details, right? So it's possible to say 0 equals some value, 1 equals some value, 2 equals some value, where 0, 1, and 2 are the indexes of the array. All right, so that's the basic array stuff, right? Don't forget strings are just arrays of char where there is a literal 0, right? So \0 to mark the end of the string. So there's our string. Here's our array of char, right, representing the string sys220, right? So there's 7 letters or 7 characters in that string, right? The length of str, though, is 8 because there is the extra null terminator at the end of the string, right? There's the compiler inserts a \0 here for you to mark the end of the string. So run that, you get sys220. So remember we need the null terminator to indicate the end of the string because C doesn't know how big arrays are. Right? So if you have a string, you need to indicate the length of the string somehow. And so the decision that the language designer just made was to use the literal number 0 to mark the end of the string. Right. Okay, so that says that str is an array of char. Right? So that means it can hold a string of length 9 in it. Right? Now remember, if you just write char string at 10, semicolon, right, the values of the array are uninitialized, so you don't know what's in there. If you put a string into that array, or if you decide to use that array as though it were a C-style string, you have to put the \0 in at the end of the string yourself manually. Right, so here I'm going to fill it up with the character sys220, right, and then I'm going to manually insert the \0, the null terminator, into the string. Right, if you forget to do that, there is a possibility that element 7, 8, and 9 of the array are not numeric 0, in which case you'll have some extra stuff in your string. Right? So if you do that, that is a properly formatted string. When you print it, you in fact get sys220. So don't forget, if you're manually computing the string yourself, to insert the null terminator at the end of the string. Right? You can have an array, an array marked const. Right? So here is here's an array of int of length 3 that's marked const. Right? So a const qualify array is simply an array where all the elements are also const qualified. Right? So what does that mean? It means x0, x1, and x2 are all const. So in other words, you can't change their value. They're read-only. You can initialize their values, but you can't change them afterwards. Right? So this initializes the elements to 1, 2, and 3. Right? You're allowed to look at the value at index 1. Right? So this works fine. Right? So that says 2 is stored in x1. Right? You're not allowed to attempt to write to an element of the array. So if you try to write to the element at array index 1, you get an error, right? And it tells you assignment of read-only location x1. Right? So if you have a const array, you have to initialize the array elements yourself. You have to initialize the array elements, right? There's no way to assign to them after you've created the array. And finally, don't forget that you cannot assign to array variables. Right? So here's x and y. They're two arrays of length 3. Right? They're both arrays of int. Right? If you wanted to copy y into x, right, you cannot write x equals y. Right? That doesn't work. So if you try to do this, you get an error. Right? Assignment expression with array type. It's trying to tell you you cannot assign to an array variable. Right? So the x equals part is the problem here. Right? And so what does that mean? Well, if you want to copy an array, you have to write a loop. Or you have to call a function that can copy the memory of the array for you. Right? Strings are arrays, so that means you can't assign strings to one another. Right? Here we have two strings, hello and goodbye. It might be convenient to assign goodbye to string 1. Can't do it. Right? You'll get the same error. Right? Assignment to expression with array type. All right, so if you can't assign array variables, what do you have to do? Well, you have to copy the elements one at a time yourself. So you can use a loop. Right? So to assign the elements of y to x, right, write a loop. Right? Loop over the elements of y, assigning each element to the corresponding element of x. Right? And this works fine. Right? So when you print out x, it really is 10, 11, and 12. Right? All right, so when you're, arrays are very common in C, right? It's the storage type that it's the type that you'll use to store a bunch of stuff. And so it's not surprising that there are functions that copy memory for you so that you don't have to write this loop, right? So to avoid writing this loop every time, right? So to copy a string or to copy an array of stuff, right? Just use a function to copy the contents instead. Right? And so the function memcopy is the function that you would use to copy a chunk of memory from one location to another. Right? It's declared in string.h, which is a bit odd. You wouldn't think that a memory copying function would be declared in the header file string, but that's where they put it in the early days of C, and so that's where it lives. That's where it lives now. So how does this thing work? So you pass in a pointer pointing at the start location where you want to copy from. Right? So that might be the name of an array, for example, if you wanted to start copying from the front of an array, at the first element of an array. Right? Notice that it's a const pointer. Right? Also notice the pointer type is void star, so it can point at anything. Right? By marking this pointer as a const, it means that the function promises not to change the elements being pointed at. Right? So in other words, it's not going to change any of the elements in this array src. Right? Count is deceiving. Right? It's not the number of elements you want to copy. Right? Even though it's called count, which is silly, but that's the way it works. Right? So memcopy says it copies count number of bytes. Right? Where a byte is the size of a car. So if you wanted to copy, say, 3 ints, right? For count, you would write 3 times size of int. Right? So you have to remember the count's not really count, right? It's the amount of memory that you want to copy. Right? The amount of memory that you want to copy is equal to the number of elements you want to copy times the size of each element. Right? So that thing there is almost always something times size of something else. Right? Dest is where you want to copy into. Right? So it's a pointer pointing at the first element of the array where you'd like to copy into, or the starting element of the array where you'd like to copy into. Right? So for example, here are my 2 arrays, x and y. Right? I would like to copy the contents of y into x. Right? And so I need my source pointer. So I need a pointer to the first element of y. Right? So I can get the pointer to the first element of y by writing address of y0. You could also just write y. Right? Because remember, the name of an array is synonymous to a pointer to the first element of that array. Right? I now need my destination pointer. So where would I like to start copying into? Well, I'd like to start copying into that element there. Right? And so I can get that address by just writing address of x0. You could just write x as well. Right? So now I'm going to copy from here into here. How much memory would you like to copy? Well, I'd like to copy all 3 elements. How big is each element? Each element is the size of an int. Right? And so that's how you copy 3 int elements from the source array into the destination array. Right? Does it work? Yeah, it works, right? So you get 10, 11. So when you print out x, you do in fact get 10, 11, and 12. Right? Now, the thing you have to remember with this function here is that that's a pointer and that's a pointer, right? They don't have to point at the first element of either array, right? They can point at any element you like, right? And it'll start copying from whatever is being pointed at, right? And it'll copy into whatever is pointed at. So you can copy from the middle of an array, and you can write into the middle of an array, right? You just have to adjust your pointers. Okay, so here's a slightly more complicated example, right? X has room for 6 ints, right? Y has room for 10 ints, right? I would like to copy 0, 1, 2, 3, 4. How many elements? 4. I would like to copy those 4 elements from Y into these 4 elements of X, right? So those 4 elements here into these 4 elements here, right? So what is my destination pointer? So I need a pointer to that element there, right? So that's the element Y4, right? So I can take the address of that, and that's my source, right? I would like to start writing into the 3rd element of X, right? And so the 3rd element is x2, right? Take its address, right? I'd like to copy 4 ints, so 4 doubles in this case. So 4 times size of double is the amount of memory that I'd like to copy, right? And if I've done this correctly, x should be the array 0, 0, 14, 15, 16, 17. And it is, right? So 0, 0, 14, 15, 16, 17. So the source and destination pointer, they don't have to point at the front of an array or at the start of an array. They can point anywhere into the array, which means you can copy from and into any array, right, wherever you like. Strings are represented using arrays. So you could use memcopy to copy strings if you wanted to, right? Definitely possible. You just have to remember to also copy the null terminator when you do it, right? But because strings are special, there's actually a function that can copy strings for you, right? So string copy is the function that you would probably use to copy strings, right? It works more or less the same as memcopy, except you don't have to pass in the length of the string to copy, right? The way that string copy works is it just marches along the source string until it finds the null terminator and then stops copying. Right, so when we talk about strings, we'll look at string copy and how to implement it. Okay, so this array pointer duality is a feature of C that you have to get used to. Right, the name of an array is simply synonymous with the pointer to the first element of the array. Right, so in other words, if you have an array ARR, then ARR is also a pointer, or you can treat it as a pointer to the element at ARR0. Right, so here's ARR. Right? It's an array of 3 doubles, 1, 2, 3. P is a pointer to the first element of ARR. Right? So I can compare P and ARR. Right? If what I said is true, then the 2 pointers should be equal. Right? And we should get P equals ARR, and we do. Right? And we saw this in a previous notebook, I think 2 classes ago. And so that means you can do something that sort of looks like assigning an array to a pointer. Well, it does look like assigning an array to a pointer. Right? So here's your array, str. Right? Here's a pointer p. Right? I can write p equals str without any issues. Right? Now remember, you cannot, if p was an array variable, right? So if it was char p square bracket, right? You can't write p equals str, right? You're not allowed to assign to an array variable, right? Here, p is just a plain old pointer. So you can assign to that without any issues. Right? str is just the name for a pointer to that C. Right? And so you can write p equals str without any issues. Right? Once you've got p, you can go ahead and use p like it was a regular pointer. So for example, you can dereference p. Right? If you dereference p, you get the object that p points at. That says that p points at the first character of str. So if you dereference p, you get the uppercase C. Right? So there, the variable c will be equal to the uppercase letter C. Right? And so if you print those out, right? So if you print out the if you print out p, the pointer, as though it were a string, right? It prints out that string, right? And if you print out C, the character C, after dereferencing P, right, you get the uppercase C. All right, so you might think, oh, hey, look, I can assign to a pointer variable, so maybe I can get around this problem of assigning to an array variable by making a pointer instead. Right? So here's my array str, here's my array copy. Right? I want to write copy equals str, but I can't. Right? So we know that already. So can you cheat with a pointer? Right? So can I write, so I know that I can make a pointer p and have it point to the first letter of C. Right? So I can write char star p equals str. Right? And now you say, well, hey, look, the name of the array is just synonymous with a pointer to the first element of the array. So can I write copy equals p? Right? So in other words, can I try to cheat the system? And the answer is no, you can't. Right? The compiler knows that copy is an array variable, right? So it won't let you assign to it, no matter what you try to do. Right? So you can't cheat the system by using a pointer here. Right? You can never assign to an array variable. All right. So if you've got a pointer to, so if you have the name of the array, right? You know that it's a pointer to the first element of the array, right? It might be useful if you get to the second element of the array and the third element of the array, and so on and so on and so on, right? So we know how to do that using indexing, right? I know that ARR1 is the second element of the array, right? I know if I take the address of that, well, I get the address of the second element of the array. So here I would get the address of the 2. Right? There is an alternative way to do this without using indexing. Right? So instead of using indexing and the address of operator, you can use pointer arithmetic. Right? All right. So if p is a pointer to an element of the array, right, then p plus 1 is a pointer to the next element in the array. Right? P minus 1 is a pointer to the previous element of the array, if such an element exists. Right? So more generally, if you have a pointer p that is pointing at an element of the array, so in this case it points at ARRJ, right? Then p plus I points at the element ARRJ plus I. Right? P minus I points at the element ARRJ minus I. Right? So in other words, this plus I simply is a pointer I positions to the right. Right? P minus I is simply a pointer I positions to the left. Right? If you want to dereference, right? If you dereference that pointer, right? Then that's the same as getting the element at ARRJ plus I. Right? And if you dereference this pointer, that's exactly the same as getting the element at ARRJ minus I. Right? So indexing and pointer arithmetic are more or less, you can replace indexing with pointer arithmetic. Right? So if ARR is the name of an array, ARR plus I is a pointer to the element at ARR index I. Right? So here's our array. It's got 7 elements in it. Right? This is a pointer to the 4th element of the array. Right? So it should point at the 3. Right? If I write p plus 2, that says go 2 elements to the right. Right? So that's a pointer to the 5. right? If I dereference that, I'm going to get 5.0, right? And that's the same thing, right, as writing, remember P is a pointer to ARR3, right? So P plus 2 is a pointer to ARR3 plus 2, so ARR5. Right? P minus 3 is exactly the same as a pointer to element 3 minus 3, at index 3 minus 3, right? Or the first element of the array. Right? So the first one is the 5, right, up here. Right? The next one is the 0, so that's this line right here. Right? Can you change any element of the array? Sure, right? Just take your pointer. So I'm going to change the 7th element of the array. ARR is is the name of the array, right? So it's a pointer to that value there. ARR plus 6 is just a pointer to the 7th element of the array, or the element at index 6. This should be change ARR. I just realized that. There we go. Right. And so ARR plus 6 is just pointing at the, so there's ARR plus 1 plus 2 plus 3 plus 4 plus 5 plus 6. So we're going to change the 6 to minus 100. Right? And notice that after you run that line, right, ARR6 is now minus 100. Right? And so there's that's how pointer arithmetic works when you have a pointer into an array. All right, so I guess 2 lectures ago I told you there's something called the too-far pointer. Right? So the too-far pointer is given an array of length n. The too-far pointer is a pointer to the element at ARR plus n, right? So in other words, it's the n plus 1th, a pointer to the n plus 1th element of the array, which doesn't exist, right? So remember, for an array of length n, your largest index is n minus 1, right? The C standard says, though, you are allowed to form the pointer ARR plus n. Right? So in other words, you can take the address of the element at ARR index n. Right? You're not allowed to use it for anything. Right? So you're not allowed to dereference that pointer, right? Because it's one past the end of the array. Right? So that pointer there is simply the pointer that points exactly one element past the end of the array, which is why it's called the too-far pointer. Right? The reason the standard says this exists is because there's a lot of C code kicking around that assumes this thing exists, right? So in other words, people iterate over arrays, right? Assuming you can advance the pointer one past the end of the array, right? And so we'll, in a second, in a few moments, we'll talk about how you iterate over array elements using a pointer, right? And then you'll see why the too-far pointer has to exist. Right? But remember, you can't dereference it, right? It's like trying to access an element that's past the end of the array. Right? Almost certainly bad things will happen. Okay, so pointer comparisons. You are allowed to compare pointers for order. Right? So in other words, less than or equal to, greater than, and greater than or equal to, those operators are all meaningful for 2 pointers P and Q, assuming those pointers are pointers into the same array. Right? If they're pointers into a different array, then you don't necessarily know what these mean. Okay, so what is P minus Q? Right, so P and Q, they point into the array, are pointers into the array. Right, so if P is less than Q, right, that means that P is pointing at an element in front of the element that Q is pointing at. Right, so in other words, if P is pointing at ARRI and Q points at ARRJ, right? If that's true, it must mean that index I is less than index j. Right? In other words, P is pointing at an element that's in front of whatever Q is pointing at. Less than or equal to means the same thing as less than, but P and Q might be pointing at the same element as well. Right? If P is greater than Q, then it means P is pointing at an element that comes after Q, the element that Q points at in the array. And similarly, P greater than or equal to Q means the same thing as P is greater than Q, but P and Q can also be equal, right? They can be pointing at the same element, right? So in other words, you can use the less than and greater than operators to compare the locations of the 2 pointers. Right? That's true if P points at an element in front of whatever Q is pointing at. Right? That's true if P points at an element that is after whatever Q is pointing at. All right, so now we can iterate over an array using pointers. Right? So plus, plus, minus, minus, plus equals, and minus equals, these are all defined for pointers. Right? So P points into an array. Right? Then P plus equals n. Right? So you know what this does for ints, right? So P plus equals n for an int adds n to P, right? Changing the value of P. Right? So this does a similar thing for pointers. Right? P plus equals n changes P so that P now points at the element n positions to the right of where it was previously pointing. Right? So in other words, it adds n to P, reassigns it back to P, right? And now you've got a pointer pointing n positions to the right of P. Right? P minus n does the exact same thing, except it subtracts n. Right? So now you have a pointer pointing n positions to the left of where P was pointing at before. P plus plus. All right, so this one, the plus plus and the minus minus operators are funny in the C-like languages, right? Because it matters what side you put the plus plus and the minus minus on. Right? So P plus plus produces a value. Right? So in other words, everything that I highlighted actually evaluates to a value. It's equal to P. Right? So if you use P plus plus in a statement somewhere, right? The compiler takes the current value of P. So whatever P is pointing at now is what the value of P plus plus is. Right? It has an additional side effect. Right? So most of us use P plus plus to mean P equals P plus 1. Right? And so that is the side effect. Right? It adds 1 to P. Right? But in the expression that you're using it in, the value of P plus plus is the current value of P. Right? It's not the new version of, it's not the updated version of P, right? It's not equal to P plus 1. Right? P minus minus is also equal to P, right? But it has the side effect of subtracting 1 from P. Okay, plus plus P means add 1 to P, and now the value of plus plus P is equal to P plus 1. Right? The value of that is just the current value of P. Right? The value of that is the current value of P plus 1. Right? The value of that is the current value of P minus 1. Right? And so that's called the post-increment operator. This is the pre-increment operator. Right? Post-increment because the value is the current value of P. Right? After you've used the current value, the value of P goes up by 1. Right? Pre-increment, the value of P is now P plus 1. Right? So update the value first and then use its value. Right? This one uses the value, then updates the value. All right, so using these operators, you can now iterate over a sequence of elements using pointers. So here's my array with 7 elements in it. Right? I can take a pointer that points at the first element of the array. Right? Each time at the end of the loop, I can move the pointer 1 position to the right. Here it doesn't matter if you write plus plus P or P plus plus, or P plus equals 1, or P equals P plus 1. It doesn't matter. They all, in this case, they all do the same thing. Right. When can I stop iterating? Right? Well, I can stop iterating when my pointer, so here's P starts here. Right? Next iteration, it'll point here, then it'll point here, then it'll point here, and so on and so on and so on, right? On the last iteration of the loop, P will point here, right? Loop will run, and then P plus plus happens. So the pointer will point 1 past the 6, right? Whatever element's past the 6, right? It's now the too far pointer, right? So I want this loop to run as long as P is less than ARR plus 7. Right, because my array is 7 elements long. Right, AR plus 7 is equal to the too far pointer. Right, and so this kind of loop is very common in older C-style code. right? So the standard says the too far pointer must exist. Right? And so that iterates over the over the array, right? So going forwards, right, we can look at all 7 elements of the array. You can go backwards as well, right? So I can start at the end of the array, right? ARR plus 6. I can't start at the too far pointer, right? If you start at ARR plus 7, there's no guarantee that it's going to work, right? But I can start at ARR plus 6, right? That's just the last element of the array, right? Each time through the loop, I can decrease p by 1, or I can move it 1 position to the left, right? When do I want the loop to run? Well, I'd like it to run as long as p is pointing at some element of the array, right? So as long as it's greater than or equal to ARR, which is that pointer there, right? And so you can go backwards over the array as well, right? And that gets you 6 down to 0, right? And so there's looping over an array using a pointer instead of indexes, right? It's not that hard to do, right? So if you to convert from the index to the pointer version, right? Remember, with an index here, you'd have int I equals 0, right? And you would have I is less than 7, right? As soon as you use the pointer, right, you just start by initializing the pointer at the first element of the array, right? In other words, as if you were pointing at A0, or AR0, right? And instead of writing I is less than 7, you just write P is less than ARR plus 7, right? And I plus plus becomes P plus plus. All right, any questions so far? Okay. Arrays as function parameters. All right, so when you write a function in C and you want it to take in an array or you want it to return an array, you have to remember that C will never pass an array to a function, right? It never wants to copy an entire array and hand the array to a function. So instead what happens is the array always, we say it decays to a pointer to the first element of the array, right? And so all that means is that if you write a function whose parameter is an array to int, right, then the compiler simply rewrites that so that it was a pointer to an int element instead, right? So one implication of the fact that an array always decays to a pointer to the first element, right, is that a function never knows how big an array is, right? This function here can never know how long ARR is unless you provided extra information about the length, right? So unless you have another parameter that includes the length of the array, right? Why? Because it simply decays to a pointer, right? And if it decays to a pointer, there's no way for the language to know when is that pointer, what happens when you advance that pointer too far, right? There's no way for it to know how long the array this pointer is pointing at. What's the other problem? So way back, like several weeks ago, right, I showed you that if you have a little local array, right, you can compute the length of the array by using size of, right? So if you take the size of the array and divide by the size of the element, for a little local array or for an array that has automatic storage duration, you can get the length of the array this way, right? It doesn't work here, right? That thing there, right? Remember, the compiler simply rewrites that as int star p, right? So in other words, you get a pointer to the first element. So when you take the size of ARR, right, that's just the size of a pointer, which on my computer is always 8, right? So you never get the right size here. If you run this program here, so I pass it in an array of length 100, and I run this program, right? First of all, you get a warning, which is good, right? The length of that is 2, right? Because the size of a pointer on my machine is 8. The size of int on my machine is 4, right? 8 divided by 4 is 2, right? So that's the size of the pointer. It's not the size of the array. If you were to write the same code here using x instead, you would in fact get 100, right? But because this function ends up with a pointer and not the array itself, right? There's no way for the language to figure out how big the array is. right? So never, ever, ever do this inside of a function, right? Never try to find the length of an array that's passed to the function, right? The only way that you can deal with this is to either include an extra parameter in the method, in the function, where the user tells you how big the array is, right? Or you have a special value in the array that marks the end of the array. Those are your two solutions, right? So when you want to write a function involving an array, right, almost always there's an extra parameter for the length of the array, right? Occasionally, like for C-style strings, right, you can require that the array uses a special value to indicate no more elements in the array, right? So that's why strings use \0, right, or numeric value 0 to indicate the end of the string. So if you wanted to write a function that finds the maximum element of an array of int, right, it's probably most convenient if you add a second parameter that is the length of the array, right? So the user has to tell you their array and the length of the array that they're searching over. Right. So this one is a const array, right? So remember what const means when you slap it in front of an array. It means the elements are read-only. So this function here is promising not to change the elements of ARR, right? So if you ever see const in front of an array name or a pointer name in a function, the function is promising it's not going to try to change the elements of that array. Right? And so what does the function look like? Well, you're just searching for the max of an array, right? So you all know how to do that. So how do I search for the maximum element in X? Well, I just call max X, right? It's C, so I have to say how long the array is as well, right? So max X 5, right? And that prints out 99. Now, one of the side effects of this is that you don't have to pass in the true length of the array, right? So for example, if you wanted to know what is the maximum element in the first 3 elements of the array, you can call max with 3 instead, right? And it tells you it's 99, right? With 2, it tells you it's 5, right? And with 1, it tells you it's minus 5, right? So there is a small advantage of doing this as well, right? You can actually specify how much of the array you want to search over. All right, so so remember, if you're going to write a function that takes in an array, right, usually you're going to include a parameter that is the length of the array. For strings, we don't include the length of the string. We instead search for a special character in the string. All right, what happens if you want to return an array from a function? So returning an array from a function has the same problem, right? If a function returns an array, then the returned array simply decays to a pointer to the first element of the array. Right? So this has the same issues as passing an array to a function, right? If you return an array from a function, there's no way for the caller to know how long is the returned array. Right? Okay, so how do we solve this problem now? Right? So now you have the problem where you need to return 2 pieces of information to the caller. Right? They need the returned array. They need to know how long the length of the array is. Right? And so you can use the techniques from the pointer notebook to solve this problem. Right? So you can return the array as a pointer, right? And then one of the other parameters of your function is a pointer to an int or a size t variable that the function can write into the length of the array, right? So that's option number 1, right? Add yet another parameter that the function can use to store the length of the array in. Right? Option number 2. You're going to return an array, right? And the array that you return uses a special value to indicate that there's no more elements in the array, right? So for example, if you return a string from a function, you can simply return the string, making sure you mark the end of the string with \0. Right? Of course, you don't have to return the array. You can return the length of the array instead, right? And one of your parameters is and the caller gives you an array that they've already allocated that your function can fill in the values for, right? So these are quite different. The first two let you make a new array in the function and return a pointer to that new array. Right? This one forces the caller to make the array for you, and your function fills in the values of the array. Right? There's yet another way to do this. Right? You can return the length of the array, and you can return a pointer to the first element of the array. I never show you how to do that in this course, but it is possible to do it that way as well. Right? Actually, it's the fourth option right here. Right? So you can return the length of the array, and you require the caller to supply a pointer to a pointer, right? In which you can return the new array. Right? So what's this one? Oh yes, incomplete example of the first option. So option number 1. Add another parameter that the function can use to store the length of the array. Okay, so here's some func, right? It's going to return an array, right? Having some length, right? Length y, right? I'm not going to show you the details of how this works because we're not ready for that quite yet. Right? So we can't return an array. If you try to write int square bracket here, the compiler will complain, right? To say you cannot return an array variable from a function, right? So instead, what you have to return is a pointer to the first element of the array, right? This is it's not a string; it's an array of int. So we have to tell the caller how long is this array, right? And so the way that we're going to do this is by forcing the caller to give us a pointer to a size t object where we can write the length of the array into. So they're going to give us a pointer to a size t object that the function can write into, right? So we're going to store the length of the array, y, right, in whatever is pointed at by len, right? So dereference len, right, and store the value y in that variable. Oh wait, we're over time. Someone should have said something, right? Okay, so when you call the function here, is this max? Oh wait, this is all messed up here. I have to fix this. All right, so I'll come back and review this example in the next class. Sorry about that.